All right, welcome everybody. I'm Dan Powers, Executive Director of the Society for Science at User Research Facilities, and we're getting started on our next two sessions here at the 2021 annual meeting. Our first session is actually going to be regarding ESNet, and I'm just double checking here. We are expecting any moment our first speaker, Eli Dodd from ESNet. And thank you. I also see that Dr. Jeff Blanchard is here. He was going to be coming on right after Eli at just about 1:30 Eastern Time. And Jeff, if you want, you can put your video or turn off your video. It's up to you if you'd like to be engaged digitally or not. Hello, Eli. Thank you for making some time for us today.
Hey, how's it going, all?
Very good. Let me give a quick introduction to you here, and then we'll turn over the screen share to you. Tell us what we should be knowing about ESNet's plans.
All right, sounds great.
All right. ESNet is the high performance networking facility of the Department of Energy Office of Science, and ESNet interconnects the entire DOE National Laboratory complex, whether you know it or not. As I've heard from some scientists, this might be a behind the scenes thing regarding their data transfer, and they didn't even know that ESNet was the system. The facilities that ESNet covers, as I say, is throughout all of the user facilities of DOE, but it's going to be growing, and there's more detail that we're going to hear about today. Eli Dart is the acting group leader, ESNet Science Engagement Group, and he is going to describe how ESNet is already being used and the new state-of-the-art network ESNet is building, and the science capabilities enabled by ESNet that can be tailored to support this whole community. Eli, over to you.
Thanks, Dan. So let me share this. Hopefully you all can see that. So I'm going to talk a little bit about the ESNet facility. And I'm going to talk, Dan, as you mentioned, about our next generation network. Talk a little bit about the ways in which scientific user facilities and science projects and science programs can make effective use of this networking facility that we operate here at ESNet. So everybody needs to show a picture of their thing, and no networking talk is complete without a network diagram. This is a notional network diagram. So what is ESNet? ESNet is the high performance networking facility of the DOE Office of Science. We interconnect the entire National Laboratory complex, not just the Office of Science labs. And we connect those laboratories both to each other, but also to the rest of the science networks in the world. This includes Internet 2 and the US regionals for US university connectivity. And then, as you can see there, we've got a ring in Europe. This gets us to Geneva for the Large Hadron Collider, and then to the major peering points in London and Amsterdam for connectivity to all of our European collaborators. And so, you know, we also have some Pacific connectivity, which I'll talk about in a moment. So we're a network, right? And we're built on the same sort of protocol stack as the internet. We are actually engineered to support scientific applications specifically. So we use TCP/IP. We're not your Comcast. We're not your AT&T, right? We're engineered specifically for science applications. And that connectivity is a big part of our success. So I mentioned our ring in Europe. We have peering, which is the way in which networks interconnect with each other at a whole bunch of different locations, including down the US West Coast to get to Asia. But then in Denver, we connect to NCAR. In Chicago, we're present at the Starlight Exchange, which is a significant exchange point for all sorts of science connectivity. Same in New York, Washington, DC, and so on and so on. So in fact, most of the traffic that comes to or from ESNet has one side of it that's outside of the Department of Energy Office of Science. So this is users of user facilities, right, and collaborators of national lab scientists moving data in and out of the National Laboratory complex or the facilities at those labs. And so, we're carrying a lot of data. This is actually, I couldn't find a more recent version of this slide. My apologies. This is an older slide, but we're an exascale network today. And if you look at that growth rate, it's pretty eye-watering. So, we have to run pretty hard to stay ahead of all the good work that our users are doing. And that's great. We like it that way. Because what that means is we're serving our mission, which is to enable data-intensive science at the national labs and at the user facilities. So to continue to meet the demands of that growth and the demand for more advanced services, we're building a new version of the network, ESNet 6. So not only do we see that huge data growth curve that I just showed you, right? So that's just sort of a speed and capacity need. There's increased needs for reliability and resilience. Why? Because at this point, the network really just needs to be there all the time. Gone are the days when stuff could go down and people could still get their work done. But then even more on top of that, we need not just IP dial tone, as we in the network engineering community call it, or basic routed connectivity. We need advanced services. We need the ability to engineer paths that have specific quality of service attached to them. And so this next generation of the ESNet network continues our history of innovation in this space. So this is a state-of-the-art optical network built on carrier-grade technology, but it's built again for scientific applications, and the features and services that the ESNet network provides are derived from the needs of our science constituents. So we have a requirements program whereby we collect requirements from the 6 program offices and the DOE Office of Science. Now, this isn't just fill out a survey or something like that. It's a hands-on and frankly labor-intensive process where we engage with the stakeholders both at the program level, at the facility level, but also individual scientists and PIs to figure out how they're using the network and what their needs are. And we derive the services that ESNet provides, as well as do capacity planning from that information. So based on all of this, what are the design objectives for ESNet 6? So I mentioned reliability and resiliency. We want there to be no single points of failure within the network at all. And so this casts its shadow on topology. It casts its shadow on the hardware that we use, the software that we use, right? So we're really designing this so that it doesn't go down. We want to be agile in the way that we can do moves, adds, and changes in terms of where you need bandwidth. But we also want to be able to do that at a fine grain of detail. So we've got the technology stack available to do that. We want to be able to automate this. That helps with resiliency. It also helps save staff time. And then as I'll talk about in a moment, there's a flexible service edge that is highly programmable, and that allows for more advanced capabilities than just your sort of normal destination-based IP forwarding. So the basic architecture that enables all of these features is what we call hollow core and a service edge. So the hollow core its job is to be resilient and scalable and get the packets where they need to go, right? The service edge, that's where all the smarts are. And so if you need specific fine-grained services, you need telemetry, you need dynamism, right? That we can do that at the network edge. And so this sort of two-phase architecture here, or two-layered architecture, provides a lot of benefits, both again in terms of resiliency and in terms of smarts and intelligence. So an example of what we can do at the edge there, right, is this thing which we call high touch. So this allows us to do things like get fine-grained inter-packet timings if we want to do protocol research, or tailor a service specifically for, say, a caching service, or some other specific real-time workflow that needs to happen at a facility. So this is an example of the kinds of things that we can do at that edge. And if you need multiple edges involved, that's fine. They're interconnected by this incredibly performant, resilient hollow core. So I said that science networks are built specifically for science applications, as ESNet does. This difference is actually kind of stark. So it was great. There were some folks who did some tests over the commodity internet for like high-speed data transfers. And the commodity network providers thought they were denial of service attacks and shut them off. It was pretty entertaining, actually. Whereas for a research and education network, R&E, this is like normal stuff, right? We should support this and it should go as fast as possible. So we want to engineer for zero loss. There's a bunch of other things that go into this, and a full discussion of the protocol dynamics is sort of beyond the scope of this talk. If you'd like to go into that, I'd be delightful to do so. But the key point here is that we're engineered to support science specifically. That's our core mission, and it has been our core mission, in fact, for decades. So that mission gets us to the science DMZ model. So again, this is out of, I don't want to go through the details here. I don't really have time, but if you'd like to talk about it, I'm more than happy to, or you can go to the link there, right? If you just Google for faster data science DMZ, you'll find it. So this is a high-speed, loss-free, friction-free network path, dedicated hosts for data transfer, and monitoring and measurement to ensure consistent performance, and then engagement with the scientists to help them use this infrastructure effectively. But this is the substrate, right? So this is built at the edge of a science network. So ESNet connects to the national laboratories and the facilities. The facilities would deploy a science DMZ. Many of them have, and I'm going to go through now some of the benefits that come from doing that in the ability of their scientists and users to more effectively use network infrastructure like ESNet. And if this is a thing where you don't think this is happening at your facility, please contact us, and we can work with your national laboratory networking staff and your facility networking staff on either identifying it if it's there, or helping them design it if that's what they desire to do. So this is an abstract cartoon of what a science DMZ looks like. It's just a little network enclave, but it's designed for high performance. Once you have that, you can start doing other things. So as an example, this is the Pedestal DTN project, right, built on top of the science DMZ model. So the science DMZs at Argonne, Berkeley, Oak Ridge, and also at NCSA, which is the NSF-funded, one of the NSF-funded centers. They got their DTN clusters. They have big DTN clusters with really big file systems, because like they're supercomputer centers, right? We wanted to get the data transfer performance up in a sort of rising tide lifts all boats kind of way. And so after some work, we were able to do that. And at this point, routine Globus transfers, and actually today's numbers are faster than this. So this is the graphic from the end of the project. But if you look, some of those transfers are 50 gig in one direction, right? And this is not a benchmark friendly data set. If you look at the data set composition there in the lower right, I mean, there's some 0-byte files in there. There's a few, larger than 10 gigabyte files in there. The size distribution is large, and it's, a little over 19,000 files and a little over 200 directories, right? So this is not a benchmark data set. This is real simulation output from a real cosmology code, right? So this is the type of stuff you would expect users to do, and it performs really, really well. So this is the kind of thing you can do if you engineer the edges of a science network well. And so the science network then facilitates this sort of jump in performance. Another example of this is a data portal. So if you're serving data, or you're publishing data out from a collection, say for climate science or genomics or something like that, the classical way of doing this is you just hook a web server up to the file system and away you go. That's like really Y2K way of doing it. And we can do things a lot better and a lot more scalably now, right? So instead of using this sort of legacy design where you just say, okay, I'm going to stick a web server in front of my collection of data, and you can go clicky in a web browser, and maybe you might get the data that you need someday. You can hook this up to a science DMZ DMZ instead, and then you get all the advantages of the infrastructure I was describing before. So a great example of this is the Research Data Archive at NCAR. We routinely see transfers to and from the DOE supercomputer centers and the data portal infrastructure at NCAR, and it's 50 gigabits or faster. Right? It worked really, really well. So it really improved the scale of data that the scientists can work with. And so the reasons to do this, right, it's pretty obvious. Why would you want to do this? Well, data set sizes are growing, data object sizes are growing. There's a lot more of them. But the way in which scientists use data has changed significantly in the past decade or so. And there's huge, I think, untapped potential in making the data sets of a field available to HPC by means of a high performance data portal. And so a couple of examples here, right? So this is a screenshot of the press release from the first exascale science run, right? Done by Dan Jacobson and collaborators on the Summit supercomputer at Oak Ridge. This was a genomics data analysis application, right? Another is going through large climate data sets and finding atmospheric rivers in those data sets and understanding how that changes in different carbon scenarios or how different models produce different outcomes and what that means for the science. But again, these are very large data analysis efforts. And so groups like that, right? They don't need like the little tiny subset of the data that you can download to your laptop via a web browser, right? They need all the data that matches the query for the kinds of stuff that they're interested in. They need to aggregate all of it next to a big machine and use a really big machine to grind through all of it. So this is a fundamentally different paradigm than the legacy data portal design was built for. And so there's a huge amount of benefit to doing this work at the edge where you modernize the data portals, connect them up to science DMZs so that the data in those portals is also usable by computing resources hooked up to science DMZs. But it's not just about big data sources in terms of data publication or data portals. We're also talking about instruments here. So the super facility model now is connecting computing to experiment by means of a high performance network in a way that allows the computing to be used in real time or near real time to inform and enhance the productivity of the experiment. And so the idea there is, so I've got a bone sample and I'm characterizing it at a light source, and I mount the thing, put it in the hutch, close the interlock, take some data. I want to know if I've gotten good data before I go to all the work of taking that sample out of the hutch and putting a new sample in. So if I can get a quick rendering that comes, so this is not publication level data analysis, but it's enough analysis that can happen quickly to help guide the experiment so that I know whether I got good data out of that sample. If I did, I can move forward, right? Because beam time is hard to come by and it's expensive. This is making the entire National Laboratory complex work for me as an experimenter in a way that allows me to be more productive in getting the data that I need from the samples that I have in the beam time that I have. So another example of this is the LINAC coherent light source at SLAC. There's an exascale project called XFL, which SLAC and NERSC, the computing center, and ESNet are all working on for exactly this sort of workflow. And these folks can move huge amounts of data, but it's productive in the way that they do it. And they catch alignment errors. They verify that the work that they've done is good, so they can move forward. And so this is being engineered with a modern software stack. It's a really amazing project, and it's an example of this super facility model. So I'm just going to start to wrap up here. So you can really think of ESNet as the data circulatory system for the DOE Office of Science, right? For the national laboratories, for the user facilities, right? We're a mission network built specifically for scientific applications. We're there to accelerate science, right? We want to make you and your users more productive. And our whole goal is to create a world where scientific progress is unconstrained by geography, right? We don't want the physical location of any aspect of the science infrastructure to matter, right? So that's ESNet's vision. That's how we build the network. That's why we build the network. From there, I will be happy to take any questions you might have. Thanks.
Okay, all right. Thanks, Eli. I'm intrigued. You brought up so much data there, and I'm curious if any of the guests on the call are not scientists at user facilities and were aware of how their organization might be tapping into ESNets. I'll wait and see what kind of questions come in. I had a question for you regarding the aim of having no single point of failure within your network that you were describing. I was curious if there's a relevant or significant realm of data sourcing that could become a problem in terms of data management, or if it really is a topography or other type of outside force that you see as being the threat that's a concern.
So let's see. It depends on what layer of the stack you're talking about, right? So if you're talking about connectivity between two intermediate routers in the network or between two optical systems, the thing that you're worried about is train derailments, backhoes, on construction jobs, these sorts of things that like cut fiber cables. And so what you want is what we call geographic diversity, right? So, and that gives you resilience, because if Eli's out there driving his bulldozer and he does the bad thing, the network can reroute, and the internet protocols are designed to deal with that sort of thing far faster than humans can, right? So there's a bunch of resiliency there, provided you have done the engineering work to provide that protocol stack with the failover path. If you have a single point of failure, well, there's nothing for it to fail over to, because it's out of options at this point. I cut the last cable, right? Oops, right? So doing the engineering work up front to build in geographic diversity is a big part of that. As you go further up the stack, you start to get out of the realm of what is native networking protocols and further into the application space. And so now you start getting into places where you want to say, okay, well, if I have a data repository, what I really want is geographic diversity, right? Two geographically distinct storage systems that can each present that data if either one of them goes away. So you have a primary, secondary, active, primary failover, however you want to talk about that. So like the JAMO infrastructure that JGI facility uses is a great example, right? So you go talk to the front end, JAMO knows where the real data objects are, and they can be on tape, they can be on disk, whatever, and it will still serve them to you. And they're working on making that site diverse, right, to deal with exactly those eventualities. Now, there are other cases where the data sets are just so large that it's hard to make them geographically diverse. And so what you do then is you make the storage system highly redundant and reliable, right? So that's at a different layer of the stack. So it really depends on where you're doing the engineering and what the other constraints are as to exactly how you achieve that.
All right. Well, and along those lines, I was curious if you're seeing sources of data that will take advantage of this type of efficient network you're creating. Is it coming from bioscience or from other types of energy and that realm of research, or things going on in aerospace? Is there sources that actually seem to be putting, if not a strain, at least a demand on the network?
Oh, yeah. You bet. So the poster child everyone trots out first is the LHC experiments. They are a very heavy user of our network infrastructure. They can flatten circuits, no problem. But there's a bunch of work that's being done at computing facilities. So like I said, right, the Office of Science supercomputer centers, right, the Oscar computing facilities, they are capable of moving huge amounts of data, and they do routinely, right? It's not just we could do this if we wanted to, right? It's, if you just go and look at routine user activity, oh, look, somebody just slung a couple of 100 terabytes around because they needed it to be somewhere else in order to do their job, right? And that's great. This is the kind of thing we need to enable, because if we can't enable that, then immediately somebody's stuck, right? And now they're like, I got to spend a month data wrangling instead of just like, go into a simple GUI, click, click, click. It's there by lunchtime. You know, by the time lunch is over, it's done. And I can go like work with it now, which is really, I mean, people are our most precious resource, right? The machines should work for the people, not the other way around. But we're also starting to see a bunch of other stuff. We've got a 5G effort going where we're going to instrument a watershed. And so, you know, pull data in from sensor network. There's a lot of different stuff going on, and ubiquitous, high speed data scale connectivity is the lifeblood of getting all of this sort of stuff done. This is why I like the circulatory system analogy, right? It's just the circulatory system has to be reliable. It's got to go fast, and it's got to be customizable and yeah, you got to be able to make it do what you need to do. That's what that service edge, right? The high touch services edge is all about, right? Yeah, we've got this big beefy thing, but we can make it work for you and do exactly what you scientists need, right, to get your next Nobel or whatever it is you're working on.
Great. Okay, how do people reach you, or what kind of website would you tell them to look at first?
So let's see. You can send email to engage@es.net. That's my group. And we can put you in touch with whomever you need. Our website, www.es.net. You can learn about the network. Our knowledge base for network performance is fasterdata.es.net. Okay. So those web links are in the slides.
Well, thank you very much then for this overview, and I appreciate you making this time. And you can stick around if you would like up on screen, or if you've had enough Zoom time. Not required, but thank you again for your time this afternoon.
Thank you for the opportunity, and again, I welcome conversation with anyone in the facility space. Delighted to work with you.
Okay.